Chapter 4, Motion. This lecture will help you understand acceleration, using vectors to solve problems, and to analyze motion of an object in free fall. Galileo first formulated the concept of acceleration in his experiments with inclined planes. A ball rolling down a slope had its speed increase. A ball rolling up a slope had its speed decrease. A ball rolling on level ground did not change its speed. Acceleration is the rate at which velocity changes with time. We define acceleration as the change in velocity divided by the time interval over which the change occurs. It is delta V divided by delta T. Rewrite our basic equation as delta V equal A times delta T. The change in velocity may be in magnitude, in direction, or both. A car rounding a corner is changing direction, which means its velocity is changing. Since the velocity is changing, the car is undergoing acceleration, even if its speed does not change. A McLaren P1 goes from 0 to 180 miles per hour in 15.8 seconds. What is the acceleration in feet per second squared? The basic equation is delta V equals the acceleration A times the time interval, delta T. The working equation solves the basic equation for the acceleration. We have to convert 180 miles per hour to feet per second. Since there are 3,600 seconds per hour, we divide by 3,600. Since there are 5,280 feet per mile, we multiply by 5,280. This yields 264 feet per second. The initial velocity was 0. The final velocity is 264 feet per second. The time interval is 15.8 seconds. The acceleration is 264 feet per second divided by 15.8 seconds, yielding 16.7 feet per second squared. The figure shows the motion diagram for acceleration. The car is speeding up with a constant acceleration. Note how the distance covered and the velocity change during each time interval. The acceleration for the last interval is calculated. The final velocity was 15 meters per second, and the initial was 3 meters per second during the 1 second interval. The acceleration is 3 meters per second squared. Note that the acceleration is positive. Acceleration is a vector, and in this example, the direction of acceleration is in the same direction as the velocity. This is not always true, and we will have other examples to show this. In this motion diagram, the car is slowing down with a constant acceleration of 10 meters per second squared. Note how the distance covered and the velocity change during each of the time intervals. The acceleration is calculated for the first interval. The initial velocity is 30 meters per second, and the final velocity is 20 meters per second in a time interval of 1 second. The acceleration, in this case, is negative, which is commonly called a deceleration. When an object is slowing down, the direction of the acceleration is opposite the direction of the velocity. A plane accelerates at 8.5 meters per second squared for 4.5 seconds. Find its increase in speed in meters per second. The acceleration is 8.5 meters per second squared, and the time interval is 4.5 seconds. We are looking for the change in velocity. The working equation is the velocity. Substituting what we know, the change in speed is 38 meters per second. Since this value is positive, the speed of the plane has increased by 38 meters per second. A driver lets up on the gas pedal and coasts at a rate of -3 meters per second squared for 5 seconds. Find the new speed if the original speed was 20 meters per second. We know the acceleration, the time interval, and the initial velocity. The acceleration is negative because the car is slowing down. The working equation is the change in velocity. We need to keep in mind that the change in velocity is defined as the final velocity minus the initial velocity. The final velocity is the initial velocity plus the change in velocity. Substituting what we know, we find the change in velocity is minus 15 meters per second. Negative since the car is slowing down. With an initial velocity of 20 meters per second and a change velocity of minus 15 meters per second, the car is slowing down, so the velocity is decreasing. The final speed is 5 meters per second. Uniformly accelerated motion of an object occurs when its acceleration is constant. Examples are a ball rolling along a straight incline, a car increasing its speed at a constant rate, and a ball dropped from a building. These are kinematic equations, the equations used to define the motion of an object. You will find a handout on Blackboard. The first of these equations is the average velocity is defined as the final velocity plus the initial velocity divided by 2. The second, final velocity is the initial velocity plus the acceleration times the time interval, or delta v equal a delta t. The third is the change in position is final position minus the initial position, which is also equal to the initial velocity times the time interval plus 1/2 a times the time interval squared. Our fourth equation is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in position. Here are the definition of all of our variables. Become very familiar with these equations as we will be using these extensively in the course. Here are several examples. Pause the video while you work on them. 1. The average velocity of a rolling freight car is 2 meters per second. How long does it take for the car to roll 15 meters? 2. A dragster from rest reaches a final velocity of 318 kilometers per hour. Find its average velocity. 3. A train slowing to a stop has an average acceleration of -3 meters per second squared, or a deceleration. If its initial velocity is 30 meters per second, how far does it travel in 4 seconds? 4. A car accelerates from 67 kilometers per hour to 96 kilometers per hour in 7.80 seconds. What is its acceleration in meters per second squared? Here are the solutions. How did you do? The first, 7.50 seconds. The second, 159 kilometers per hour. The third, 96 meters. And the fourth, 1.03 meters per second squared. If you have any difficulties in these, please ask in class. Acceleration and velocity are actually A, much the same as each other, B, rate, but for different quantities, C, the same when direction is not a factor, D, the same for free fall situations. B, rate, but different quantities. Velocity is the rate at which distance changes with time. Acceleration is the rate at which velocity changes with time. Now we explore free fall. When the only force acting on a falling object is gravity, with negligible air resistance, the object is in a state of free fall. The distance fallen is d, and the velocity is v. The acceleration of gravity is g, and is equal to 32 feet per second squared, or 9.80 meters per second squared. The time of fall is delta t. The figure shows the time, distance falling, and velocity. At time equals 0, the distance fallen is 0, and the velocity is 0. At each 1 second interval, the distance and velocity increase. At 1 second, the distance fallen is 4.9 meters, and the velocity is 9.8 meters per second. At time 2 seconds, the distance fallen is 19.6 meters, and the velocity is 19.6 meters per second. Now you will fill in the distances for 3, 4, and 5 seconds. Did you get 44.1 meters and 29.4 meters per second at 3 seconds, 78.4 meters and 39.2 meters per second at 4 seconds, and 122.5 meters and 49 meters per second at 5 seconds? If not, we'll discuss it in class. If a falling object gains 10 meters per second each second it falls, its acceleration is 10 meters per second, 10 meters per second, both of the above, neither of the above. It is 10 meters per second. Only B has units of acceleration. A has units of velocity. It is common to express 10 meters per second as 10 meters per second or 10 meters per second squared. A free-falling object has a speed of 30 meters per second at 1 instant. Exactly 1 second later, its speed will be the same, 35 meters per second, more than 35 meters per second, or 60 meters per second. C, more than 35 meters per second. 1 second later, its speed will be around 40 meters per second, which is more than 35 meters per second. The distance fallen by a free-falling body remains constant each second of fall, increases each second when falling, decreases each second when falling, none of the above. B, increases each second when falling. See Table 1.2 for verification of this. Falling distance is approximately time squared. The table shows the velocity and distance fallen for an object in free fall at an interval of 1 second. At 0 seconds, the object is initially released and its distance fallen and velocity are both 0. Here we're using the acceleration of gravity as simply 10 meters per second. At 1 second, velocity is 10 meters per second. The distance fallen is 5 meters. At 2 seconds, the velocity is 20 meters per second, and the distance fallen is 20 meters. At 3 seconds, the velocity is 30 meters per second, and the distance fallen is 45 meters. At 4 seconds, the velocity is 40 meters per second, and the distance fallen is 80 meters. And in 5 seconds, the velocity is 50 meters per second, and the distance fallen is 125 meters per second. Here's an example. A baseball is thrown vertically upward with an initial velocity of 25 meters per second. We will assume no air resistance. A, how high does it go? B, how long does it take to reach its maximum height? C, how long is it in the air? And D, with what speed does it hit the ground? We know the initial velocity, the final velocity, and the acceleration due to gravity. Initial velocity is 25 meters per second squared. The final velocity is 0 meters per second. When it reaches its maximum height, its velocity is 0 meters per second. The acceleration is equal to g, and we call this minus 9.8 meters per second squared. The acceleration is pointed down. So how high does it go? Our basic equation is Vf squared is equal to V initial squared plus 2 times the acceleration times delta S. Rewriting this, we obtain the working equation. Delta S is V final squared minus V initial squared divided by 2A. The final velocity is 0. The initial velocity is 25 meters per second. A is minus 9.80 meters per second squared. Substituting everything, performing the calculation, we get a total distance of 31 meters. Using the ground as 0, the ball rises 31 meters to its maximum height, where the ball must stop and reverse direction. How long does it take to reach its maximum height? We will use our second kinematic equation as our basic equation. V final is equal to V initial plus the acceleration times the time interval. We rearrange to find the time interval, which is V final minus V initial divided by the acceleration. The final velocity is 0. The initial velocity is 25 meters per second, divided by the acceleration of minus 9.80 meters per second squared, give us a total time of 2.55 seconds to reach its maximum height. How long is it in the air? This involves knowing the time it takes to rise to a maximum height and the time it takes to fall to the ground. Since friction is ignored, the time to fall is the same as the time to rise. So the total time is twice 2.55 seconds, or 5.10 seconds. With what speed does it hit the ground? Since we are ignoring air resistance, the speed at impact must be the same as the speed it was thrown up, or 25 meters per second. On Blackboard is a link to a short video from the Apollo 15 moon landing. Watch the video. As we said, Aristotle did not understand friction. In 1642, Galileo began experiments and was able to reason that the cause of an object stopping its motion was friction. Consider taking a hammer and a feather, dropping them in your room. The hammer and the feather do not fall at the same rate. But the Apollo 15 video shows what happens when air friction is not present. An object dropped in air does not continue to increase its speed as it falls. Parachutists know this. Air resistance slows the fall and an object reaches terminal velocity. Terminal velocity means that the net acceleration acting on an object has reached 0. Gravity pulls down at 9.8 meters per second squared, but air pushes up at the same 9.8 meters per second squared. The two cancel and the net acceleration is 0. An object moving with a net acceleration of 0 must be moving at a constant velocity. The terminal velocity for a skydiver with no parachute is 150 to 200 kilometers per hour. After deploying the parachute, terminal velocity drops to 28 kilometers per hour. To further lessen the impact when landing, Bend your legs as you hit or drop and roll. We'll discuss this later when we discuss momentum. Terminal velocity means the force of gravity and the drag force are equal. Drag depends upon velocity squared. It also depends upon the air density, defined as rho, and the cross-sectional area A, and something called the drag coefficient, C sub d. An object with a small cross-sectional area will have less drag and will fall faster. An object with a large cross-sectional area will fall more slowly. This is why parachutists use a large parachute. The larger the parachute, the smaller the terminal velocity. The drag coefficient C sub d is something that depends on the shape and design of an object. We will use a drag coefficient of 0.5 for most things, but it does really vary. The image shows the drag coefficient for various objects. A flat plate has a drag coefficient of about 2. A cylinder has a drag coefficient of 1.2. A streamlined body, like an airfoil, 0.12. A small cylinder, again, 1.2. Consider a heavy and light person with the same size parachutes jumping together from the same altitude. Who will reach the ground first? The light person, the heavy person, both at the same time, are not enough information to tell. The answer is B, the heavy person. The heavier person has a greater terminal velocity. But do you know why? Here's something for you to try. Place a sheet of paper on top of a book. Then drop the book. What happened? Did the paper and the book separate, or did the paper and book fall together? We'll discuss this more in class.